Concept 2, using patterns to choose a model. All right, so we have looked at how to choose a model based on a graph, but making a graph is a little bit time consuming sometimes, and it'd be really nice if when we are just given a table, we can figure out a model from what we see in that table. All right, and we're going to be looking at the patterns in those tables in order to choose our model. If you have a linear equation, y equals mx plus b, each time you increase x, y is going to increase by m, right? Because I'm multiplying that by x. So if x is 1, I have 1m. If x is 2, I have 2 times m. That's where I get my common difference, right? So if I had my table and I saw that each time x increased by a certain amount, y increased by a certain amount, then I would know that those had a common difference, okay? And I'd know that I'd use a linear equation to model that data. For our quadratic equation, because we have a square, what we're looking at is not necessarily the first difference, but the second difference, the difference between the differences. Because we're going to be squaring that x value, we are going to be increasing or decreasing by a certain amount and a certain amount more each time. And that amount that we are increasing by or decreasing by the second time, the second difference, because of that squared, is going to tell us that we're looking at a quadratic equation, okay? Or we should use a quadratic equation to model our data. And then the last one, an exponential function, because we have our x as an exponent, we've got an independent variable as an exponent. Every time we increase this x, it's going to add another multiplication by this value, this b, okay, which is going to be our common ratio. So if I had 1, I would have a times b would be y. If I had 2, I'd have a times b times another b, right? If I had a 3, a times b times b times b. So each time I increase my x value, I am adding another multiplication by a value, which is my common ratio, okay? So if I look at a few different tables, a lot of you probably can see right away that this one has a really consistent, okay, same difference. We're going, oops, not plus. We are subtracting by 200 each time, right? There's 200, okay? My first differences are the same, which means as long as this is consistent, right? I'm increasing by 20 plus 20. Okay, for each of these, it's all the same. So this is going to be linear. Okay, I think linear is probably the easiest one to see, especially when I have nice round numbers. All right, these other two might be a little bit harder to see. If we look at this one, and I'm going to erase this just so I have some more room. Okay. If I look at this one, I can first of all see I am consistent with my x, right? I'm increasing by 1 each time, so I'm good to go there. And then here, I'm actually going to go backwards, starting at 100. Okay, I am going, well, maybe I shouldn't go backwards. We'll keep going this way. I'm increasing by 30. Okay, and then here I am increasing by 20, and here I am increasing by 10. Okay, as my x increases, my y increases. These are not consistent, so I know it's not linear. But if I look at this, my second difference, okay, from 30 to 20 is 10 less. From 20 to 10 is 10 less. Okay, And so because those second differences are the same, I know this is going to be a quadratic. All right. Often a quadratic is easy to find and to see if you can see the vertex in the data. But sometimes we won't have that as part of the data. So looking at the second differences is the best way to be sure. Okay. And then my last one, I can look at this and say, okay, I'm going up by 10, I'm going up by 11, I'm going up by 12.1. Okay, so it's obviously not linear. If I look at my second difference, this is increasing by 1, this is increasing by 1.1. Okay, so that's not going to work. So both of those, it's not linear, it's not quadratic. So now I'm going to look at my ratio. Well, 100 times 1.1 is 110. 110 times 1.1 is 121. And 121 times 1.1 is going to be 133.1. Okay, so I have a common ratio. And as long as these are all consistent, which they are, that tells me that this is an exponential data set, or a data set that could be modeled with an exponential equation.